Welcome to the Explainer. Today, we're jumping into the world of rectilinear figures. Now, these are the absolute building blocks of geometry, the shapes that literally make up the world all around us. We're going to break down the simple, pretty elegant rules that actually govern them all.
So what do all these things have in common? The answer is polygons. And trust me, by the end of this, you'll not only get why, but you'll start to see this hidden mathematical blueprint behind the design of so many things.
So here's how we're going to do it. First, we'll decode what polygons even are. Then we'll look at the rules that apply to all of them. After that, we'll zoom in on quadrilaterals, specifically the parallelogram family, and then we'll see how it all works in practice.
All right, let's get right into it. To understand anything else today, we've got to have a really solid idea of what a polygon is.
You know, it really just comes down to two key things. Closed, which means all the lines have to connect with zero gaps, and line segments, which just means the sides have to be straight. That's it. It's why a circle, with its curve, isn't a polygon, and why any shape with a little gap in it doesn't make the cut either.
So the first big way we split up polygons is by looking at their angles. A convex polygon, well, it kind of bulges outwards. All its corners point away from the center. But a concave one, as you can see, it caves in on itself. It's got this dent where at least one of the inside angles is bigger than 180 degrees.
And of course, here's the simplest way we classify them. We just count the sides. It's that easy. 3 sides is a triangle, 4 is a quadrilateral, 5 is a pentagon. And remember that stop sign from the beginning? Well, there it is, an octagon with 8 sides.
Okay, now this is where it gets really powerful. Because it doesn't matter if you have a simple little triangle or some crazy 20-sided shape, all polygons follow a couple of universal rules.
This formula right here, this is the master key. If you know n, the number of sides, you can figure out the sum of all its inside angles. Come on, let's try it with a square. A square has 4 sides, so n is 4. Okay, 2 times 4 is 8, minus 4 is 4. And 4 times 90 degrees, that's 360 degrees. Yep, it works perfectly. It's really just a clever shortcut for counting up the angles of all the triangles you can split a polygon into.
And what's cool is we can use these rules to work backwards too. So in this problem from our source material, we can use the relationship between the inside and outside angles to solve for n. And when you do the math, you find out the shape has to have exactly 12 sides. It's kind of like being a geometric detective.
And you want an even simpler rule, one that's almost magical? If you were to walk around the outside of any convex polygon, the sum of all the turns you make at each corner will always, and I mean always, add up to 360 degrees. A perfect circle. Doesn't matter if it's a triangle or a shape with 100 sides. It's just a beautiful, unchanging fact of geometry.
Okay, so we've got the universal rules down. Now let's narrow things down a bit and focus on the family we probably see the most in our day-to-day lives, the quadrilaterals. You know, the 4-sided figures.
Just like the name says, it's all about the number 4. 4 sides, 4 vertices, and yep, 4 interior angles that, just like our formula told us, will always add up to a neat 360 degrees.
But hey, not all 4-sided shapes are the same. The big difference maker is parallel sides. A trapezium has just 1 pair of sides that are parallel. But when a shape has 2 pairs of parallel sides, well, then you've got a parallelogram. And that's where things start to get really interesting.
So you can kind of think of the parallelogram as the head of a really important geometric family. All its core features get passed down to its very famous kids, the rectangle, the rhombus, and of course, the square.
These are the family traits, the DNA of every single parallelogram. Opposite sides, they're parallel and the exact same length. Opposite angles, identical. And the diagonals, they always chop each other into perfect halves. These aren't just random facts, they are super powerful tools for solving puzzles.
But wait a second, how do we know all this is always true? I mean, in geometry, we don't just take things on faith. For instance, how can we be absolutely 100% sure that the opposite sides of any parallelogram are equal? Well, we prove it.
And the logic here is just beautiful. Check it out. You draw a diagonal line and bam, you've split the parallelogram into 2 triangles. Now, using some basic rules about parallel lines, we can show that 2 angles and that side they share are identical in both triangles. This proves the triangles are congruent. They're basically perfect clones of each other. And if they're clones, then their other matching sides have to be equal too. It's just a flawless piece of reasoning.
This table really lays out that family tree we were talking about. See how the square, down there on the end, gets a check mark for every single property? It's because it inherits the right angles from its rectangle parent and the equal sides from its rhombus parent. That makes it the most specialized, most perfect member of the whole parallelogram family.
So what's the point of all this theory? Why does any of this stuff matter? Well, it matters because knowing these rules lets us solve puzzles that might look incredibly complicated at first glance.
Okay, let's put our new knowledge to the test. We've got this rhombus, and they've given us some algebraic expressions for its sides and one of the angles. Our job is to find x and y. It might look a little intimidating, but we have every single tool we need to crack this thing.
Okay, first things first, let's find x. What's the number one rule of a rhombus? All four sides are equal. So we can just set the expression for side AB equal to the expression for side AD. Do a little bit of simple algebra, and boom, we find that x has to be 6. Easy enough.
All right, now for the angles. This is how we're going to find y. We know the consecutive angles in any parallelogram add up to 180. So if angle A is 60, the whole angle B next to it has to be 120. But here's another special rhombus trick. Its diagonals cut the corner angles in half. So that diagonal slices the 120-degree angle perfectly in two, which means the angle inside our triangle is 60 degrees. See? We're unlocking this puzzle piece by piece.
And here it is, the final step, the big aha moment. Take a look at that triangle ABD. We have a 60-degree angle at A, and we just found a 60-degree angle at B. Well, since a triangle's angles have to add up to 180, that third angle has to be 62. That makes it an equilateral triangle. All its angles are equal, so all its sides must be equal too. Now we can set side BD equal to side AB, pop in the value we found for x, and we can solve for y. The answer is 21. Problem solved.
So there you have it. We've seen how just a few simple rules build on each other to create this incredibly powerful way of understanding the world. From the tiles on your floor to the framework of a massive bridge, these geometric ideas are the invisible architecture holding everything together. Now you know the rules, and the puzzle is just out there, waiting for you to see it.